Welcome to this lesson. My name is Sabiano from AA Tutors and Consultants. Today we want to talk about energy changes in physical and chemical processes. Life processes are either physical or chemical, and we have known the physical processes include melting, evaporation, condensation, freezing, among others. These physical processes usually are accompanied by absorption of heat energy, for example, melting and evaporation. And also they could be accompanied by release of energy, for example, condensation. In today's class, we shall focus our discussion on physical processes. During a physical or chemical process, energy is either given out or taken in. Thus, reactions are divided into two categories. The reactions can be endothermic or exothermic. In endothermic reactions, these are reactions that are accompanied by absorption of heat energy. The reactions absorb energy from the surrounding, causing a drop in temperature. Now, because of this drop in temperature, in endothermic reactions, temperatures fall around the container that when touched, it feels cold. Usually, it's accompanied by a drop in temperature. The products, therefore, are at a higher energy compared to the reactants. Now, if you look at this diagram, this one is an energy, this is an energy level diagram. Now, energy level diagram, the one that we are drawing here, if you look at the energy level diagram, you appreciate that the reactants are at a lower energy, products are at a higher energy. Now, the difference between the two is energy taken in from the surrounding. Now, because energy is taken in from the surrounding, there is a drop in temperature. There's a drop in temperature. Second category of physical or chemical reactions is known as endothermic, exothermic reaction. Now, when we talk about exothermic reaction, these are reactions that are accompanied by evolution of heat energy. That is, reactants lose heat energy to the surrounding. Now, once the reactants lose heat to the surrounding, they cause a rise in temperature. In exothermic reactions, temperature rises in the surrounding, causing a rise in temperature reading. Now, if we are doing this one practically in our laboratory, then we'll be able to observe that the reading of our temperature on our thermometer rises. Now, when they rise, it means they leave the products at a lower energy because this particular system loses energy. The reactants lose energy to the surrounding, and therefore the products are at a lower energy compared to the reactants. This information can be expressed in an energy level diagram as shown. Now, if you look at where the reactants are, reactant vis-a-vis products, then you realize that the products are at a lower energy simply because they have lost energy to the surrounding. Now, those are the two major category of reactions that we have in either physical or chemical processes. That is endothermic, which means energy is absorbed, and exothermic, which means energy are evolved. Now, let's look at something called enthalpy. Now, enthalpy, simply put, is the heat content in a chemical. Now, the heat content in a chemical is symbolized by letter H, capital, and when we want to determine the energy change in a chemical or a physical process, We do that by measuring change in temperature. When temperature rises, then we say that one is an exothermic reaction. When temperature drops, then we say that one is an endothermic reaction. Now, if you want to relate the energy of products and the energy of reactants, then we relate them using this equation here. The equation is change delta H, which means delta means change and H means enthalpy. So we say enthalpy change, this one is read as enthalpy change, is given by enthalpy change of the product minus the enthalpy change of the reactants, normally written at the end of a chemical equation. Now, the enthalpy change is usually written at the end of a chemical equation, and when it is written at the end of a chemical equation, then it ceases to be called a chemical equation. We call it thermochemical equation. If you look at this reaction here, methane gas combines with excess oxygen to give us carbon 4 oxide as one of the products, and water. Now, carbon 4 oxide and water are the products, then methane gas and oxygen gas are the reactants. But you can see the enthalpy change, or the change in energy, or the energy change, is a negative 728 kilojoules per mole. Now, basically what we are saying, if we burn 1 mole of methane in excess oxygen to produce carbon 4 oxide and water, then this one is accompanied by evolution of 728 kilojoules of energy. Now, the fact that it's negative means it is an exothermic reaction, meaning energy has been given to the surrounding. The system or the reactants have lost energy, and therefore the products are at a lower energy compared to the reactants. Now, the other one is when you dissolve sodium nitrate in water. Now, when you dissolve sodium nitrate in water, we end up with the aqueous sodium nitrate, but this particular reaction also is accompanied by absorption of heat, and the heat that is absorbed is 21 kilojoules per mole of heat. Now, if we dissolve 1 mole of sodium nitrate in water, then we end up absorbing 21 kilojoules of heat. Now, because this particular thing is denoted by a positive sign, then positive sign means energy has been absorbed, and therefore it means the products are at a higher energy compared to the reactants, and therefore this gives us an endothermic reaction. Now, I want us to move on to the core physical processes that we deal with. For example, today I want us to look at what is known as a heating curve for pure ice. Now, if you look at generally, if I try to explain what happens when you have ice and you subject it to heating, this is what happens. Now, ice will warm up. Ice that has been frozen at negative 25, it will warm up. Now, I want you to pay attention to this particular section here. From negative 25 to 0, there is a steady rise in temperature. Now, the steady rise is as a result of heating. Now, and then again, in short, if you look at this part here, this section that is labeled as ice melting. Now, some ice arrives at 0 and begins to melt, but not all of them melt at the same time, and therefore it will take some time for them to melt, for all the ice to melt and change into a liquid. Now, if you look at this particular section here, this particular section represents two things. Number one, it is the melting point, and then number two, it is a change in state. It is a place where there is a change of state of matter. Matter is changing from solid to liquid. So from this point to this point, all of it is the time required for melting. And then if you look at it, the liquid water therefore is warmed up, and some begins to start evaporating. However, most of it begins to start evaporating at this particular point here. Now at 100 degrees Celsius, water begins to boil. Now this is boiling point. The whole of it is boiling, and as it boils, the liquid water is converted into gaseous vapor. Now the gaseous water vapor begins to form from this particular section here, and it goes all the way to this particular point of the graph, after which water vapor is getting hotter and hotter. Maybe at, if we vary some physical conditions like pressure, then we might get what is called superheated steam. Now if you want to try to explain what happens, the energy changes in these particular sections of the heating curve, we get back here. Now look at this diagram. In this diagram, we have a graph of temperature against time in minutes. Now if you look at it again, we have ice at -20 that is being heated all the way to 5 degrees, all the way to 0. Now what happens between region A and B? Now between region A and B, what happens is this. In region A, temperature rises as molecules of ice absorb heat energy. Now the molecules of ice absorb heat energy, but one thing we know for sure is that ice is a solid, and therefore its particles are closely packed together. They only have limited motion, which are known as to and fro vibrations. But when heat is supplied, this heat energy is converted to kinetic energy. The kinetic energy of the particles, therefore, causes vigorous vibrations. Now these vigorous vibrations causes the particles to move further away from each other, and the moment they break away from each other, that is from the lattice, the forces that are holding the particles of the solid together, then we say they begin to achieve the liquid status. Now at that particular time, then you realize at 0, ice begins to melt, meaning it's beginning to change its state from solid to liquid. Now let's try to explain what happens between B and C. From the graph you can observe that there is no change in temperature. The temperature remains constant. Actually in this graph it remains constant from minute 5 all the way to 15 minutes. That's a period of 10 minutes in which there is no temperature change. Why is there no temperature change between region B and C? We say the temperature remains constant in region B and C. The heat energy supplied is because the heat energy supplied is used to overcome the forces holding the ice particles together. Remember, region A to B, temperature is rising constantly, steadily, but BC, the temperature remains constant because the heat supplied is used to overcome the forces holding the ice particles together, and therefore this particular heat does not cause rise in temperature. Now this point where the temperature remains constant is known as the melting point. Therefore the melting point is a temperature. It remains constant, and that particular portion is known as the melting point. Now, because we are talking about energy changes, how would you describe this heat that is supplied at this particular point? Now we say this amount of heat required to convert a given amount of a solid to a liquid at its melting point. Now you remember, this particular heat is supplied and it converts a solid to a liquid at its melting point. Now this amount of heat is known as latent heat of fusion. Latent heat of fusion. In other words, what is latent heat of fusion? Latent heat of fusion is the amount of heat required to convert a solid, a given amount of a solid, at its melting point to a liquid. Now, the solid must be converted to a liquid at its melting point for that amount of energy supplied to be known as latent heat of fusion. Now, because in chemistry our unit of measurement is moles, then how would we call the amount of heat required to convert 1 mole of a solid at its melting point to a liquid? Now that is known as molar heat of fusion. What is molar heat of fusion? Molar heat of fusion is the amount of heat required to convert 1 mole of a solid at its melting point to a liquid. Now that amount of heat that is required to convert 1 mole of a solid substance at its melting point to a liquid is known as molar heat of fusion. Now that is one energy change that we're talking about when it comes to physical processes. Now, if you look at another region, let's pay attention to region CD. Look at region CD. It's almost similar to region AB. Now, if it was mathematics, then we would say region AB is similar to region CD. Why? Because in region CD, like in region AB, the temperature rises steadily. The temperature rises steadily. The temperature rises steadily. Now, why do we observe that? Now, in region CD, the temperature rises steadily as the water molecules. Remember, at region C, all the solid has been converted to liquid. Now we have a liquid. In region CD, it's now liquid state. Now we say that the liquid at C absorbs energy, and the same thing happens. Liquid molecules are close together, but not as solids. But then again, this heat supplied is converted to kinetic energy. Now the kinetic energy increases the vibration of molecules in the liquid, causing them to move further from each other. Now as they move further from each other, they try to move into the next state of matter, which is gas. Now at D, the liquid begins to evaporate. Water liquid begins to evaporate and it begins to boil. The water at region D begins to boil. Now it boils all the way to part E. At part E, all the liquid will have turned into a gas. At part D, all the liquid will have turned into a gas, and therefore region DE is also known as the boiling point. Now, let's talk about the energy change at that point of the boiling point. We say that the heat energy supplied or required to break the forces of attraction between liquid molecules. As the liquid turns to gaseous state, that amount of heat supplied at constant temperature is known as latent heat of vaporization. We'll say it again. Now, latent heat of vaporization is the amount of heat absorbed by a substance when changing from liquid to gaseous state at constant temperature. And this constant temperature is known as the boiling point. So when 1 mole of a liquid substance at its boiling point is converted to gaseous state, then the amount of heat required, or that heat change, is known as molar heat of vaporization. Now, somebody might wonder, why do we need to know about molar heat of fusion or molar heat of vaporization? Why is it important that we know about this? Now, these two heat changes are required to estimate the strength of intermolecular forces in solid and in liquid. Now in solid, because molar heat of fusion is used to estimate the strength of intermolecular forces in solid, while Molar heat of vaporization is used to estimate the strength of intermolecular forces in liquid. Now, it is for this particular reason that we study molar heat of fusion and molar heat of vaporization. In conclusion, as we conclude, I want us to look at these physical processes. These are things that we've done them all along in science, all the way from primary school. When ice or a solid changes to liquid, that process is known as melting. Now for ice, that melting takes place at 0 degrees Celsius. Now, water to steam or liquid to gas, then we also continue heating. Now it means when you're moving from ice to gas, from solid to gas, then you're taking in energy. Energy is gained by the substances. You're taking in energy, and as you take in energy, then you realize melting takes place at a specific temperature. Boiling takes place at also a specific temperature for each and every substance that we have on Earth. Now, when you're going the reverse, then the same amount of energy that was required to convert liquid to gas is also given off. So we are saying that condensation is the reverse of evaporation. So when there is condensation, the same amount of energy that was required to evaporate the liquid is the same amount of energy that is given off when you're doing the condensation. Now the same thing we say that when you're converting a liquid to ice, what happens? The same amount of heat energy that was absorbed during melting is the same amount of energy that is given off during freezing. So now these are how these two physical processes relate, that when you're moving from from solid to gas, you're taking in energy. When you're moving from gas to ice, you're giving off energy. Now that is something that I wanted us to appreciate, and I guess that marks the end of our lesson today. Thank you very much for your time once again. My name is Sabiano, AA Tutors and Consultants. Thank you for your time.